So day 2 of equations of lines in 2-space and 3-space. Yesterday we didn't actually do 3-space, but we are going to do 3-space today. We're going to do a couple of new things today. One of those is 3-space, a couple other new things actually, and some sort of pretty important stuff. And then we're going to do more of just generally doing different things with all these different equations of lines. And I said this before, I said this yesterday, like a lot of this is just about getting us familiar with the notation and used to doing different things, going back and forth between different forms of equations, getting properties of equations, determining things about lines together, sort of asking questions about them. And it just gets us used to all of these properties and used to the notation and that kind of thing, okay? Alongside that, today we are going to learn about a couple of important new definitions and things like that, okay? But keep in mind, these few days, like yesterday, today, and the next couple of days following this, a lot of it is just about getting used to the notation and learning about how we can determine properties given these equations, that kind of thing, right? We know that for a line, what's important is where it's located in space. So, in grade 9, we use the y-intercept for that, but any point will define a line and its slope, right? Those are the sort of defining properties of a line. So if I'm looking at vector form or parametric form, how can I get those properties? How can I get the slope? How can I get, or a direction vector, we'll probably call it, right? Not slope. How can I get a point on the line or determine if a point on the line, all those things. It just gets us used to working with the notation with these equations. Okay, so let's get into this. Something we didn't talk about, I don't think at least it came up, is what we call the scalar equation of a line. And this is actually like, we called it standard form before, but now that we're comparing it to vector form and parametric form and so on, it has a new name. It's called the scalar form, okay, or the scalar equation. But it is the same as standard form, okay, where A, B, and C are going to not be fractions, that kind of thing, right? So it's called the scalar equation, and it has a direction vector. Now, you can have multiple direction vectors to a line. They'll all look different, but they'll all be scalar multiples of each other, or they will all be parallel, or they'll all be collinear, right? All the different direction vectors that you could choose. So it says its direction vector, but it's actually a direction vector for this line is going to be negative BA. Now I'm going to come back to that because I want to talk about something a little bit more important, and then we're going to come back and talk about this again. But the B and the A are obviously the coefficients of the X and the Y, and that will give us a direction vector. And getting a direction vector for a line is going to be useful, right? That's going to be something that we need. So being able to quickly get it just by inspection is going to be helpful. Now, that's one of the sort of new little pieces of terminology from today. Another one, this one's a big one, is called the normal vector. Now, we have looked at normal in the calculus portion of this course. We talked about what a normal is. And do you remember what it is? Well, you could cheat by reading ahead. A normal is a line that is perpendicular to a tangent line, right? So a normal vector of a line is a vector that is perpendicular to the line. So it has the same idea that it is perpendicular, but it turns out that when we're talking about vectors and lines and planes, in particular in 3-space, turns out normal vectors become really, really important. So it's a really useful idea and kind of a big idea, a normal vector for what we're going to do for the rest of this unit. Okay, so we need to know that that's what a normal is. So hopefully we understand that. But we also need to know how to find it, right? And this is going to depend on the form of the equation of the line that you have. So whether you have scalar or vector form or whatever, right? It's obviously going to be different. Turns out with scalar, it's really easy. The normal is just AB, okay? And So that's really useful. Scalar equation is good for getting the normal or good for coming up with if you have the normal. We often have the normal or can get it easily. So this is a good thing. This is a very good thing to know. Okay. So notice that if two vectors are perpendicular, this is a really important idea. Okay. Like we think of perpendicular as a visual thing, right? And that's fine. That's great. This is a very visual unit, definitely. So visualize it. But we also need, there's a certain idea that's really important for this unit, and generally speaking, when we're talking vectors, that if two vectors are perpendicular, then what is going to be true? Their dot product is going to be 0, right? So vector n dot vector d will equal 0. Has to. That's an if and only if. And if we think about this, vector n is a, b, and vector d, or I guess I should call it m, okay, the direction vector, m, is negative ba, so negative ba. And so this is going to be negative ab plus positive ab, so that is going to be 0. And that's why we can think of a direction vector as being negative ba. Really, in my mind at least, this is the one that I remember. I remember that the normal is going to be AB. It's just the coefficient, straightforward, no negatives, no nothing like that. And then if I have the normal, I can easily come up with a vector that's perpendicular to the normal by flipping them and turning one to be negative, right? That's the trick that we've talked about with dot product. Finding another vector that is perpendicular is easy with that trick. But you could also memorize that, obviously. Sometimes we need a direction vector, sometimes we need the normal vector. Really, what it comes down to is we need to know that if we have one, we have both. So, I might need one, I might need the other, but generally speaking, we got to know how to find both, right? We got to know the relationship between them. So let's do an example for the line with the scalar equation 2x plus 5y minus 9 equals 0. Determine the normal vector of the line. So normal is just going to be 2, 5, right? What if it said determine a normal that's a unit vector or something like that? Like again, we can add different levels to this. So the normal is going to be perpendicular just because the just because those are the coefficients 2, 5 doesn't mean that that has to be a unique normal. Um, any scalar multiple of that is going to work as well. I could rewrite this equation as negative 2x minus 5y plus 9 equals 0, couldn't I? And then the normal would be negative 2, negative 5. So again, there's not necessarily going to be one answer to this. This is the natural one that we're going to use, because why would we change it? But we can have scalar multiples of this if for some reason we need to. So if you were asked to do a unit vector perpendicular to, then you would have to do the whole turn it into a unit vector thing from the previous unit, right? And again, that's just going to get us used to these properties and used to working with these things. Determine a vector parallel to the plane. Well, what does that mean? Well, parallel to the plane, parallel to the line, I'm getting ahead of myself here. Parallel to the line means perpendicular to the normal vector, right? So that would be like a direction vector of the line. So we could get a direction vector of the line, but I can also use that trick that I can just think anything that's going to do dot with the n to give me 0 will work. So I could choose vector d is equal to negative 5, positive 2. So I get 2 times negative 5 is negative 10 plus 5 times 2 positive 10 gives me 0 if I were taking the dot product of these two vectors, right? Which the dot product of those two vectors equals 0 means they are perpendicular. Again, this is what's so important, is that we don't want to just memorize that the normal is that. We want to understand that the normal is going to be perpendicular to direction vector, and any vector that's perpendicular to the normal will be parallel to the line. Like these are all different ways of saying kind of the same thing, and you want to get to the point where you're able to just kind of go back and forth between these different ideas, right? And that's a lot of, as I keep saying, what these days is about is just working through this stuff, doing questions, getting used to all these ideas and properties and stuff. Write A, notice it says A because there are infinite different ones, right? There's not a unique equation. Write a vector equation of the line. So what do we need to write a vector equation? Well, you need a direction vector. Okay, we got that, check. And we need a position vector. So that is a vector to a point on the line. Okay, so how do we find a point on the line? Well, again, what we're going to notice is that the first time we're asked a question, the question is going to say, determine a point on the line. But the next time you're asked that question, it's not going to say that. It's going to say something like this: write a vector equation. And you are going to have to know that that means to come up with a point on the line. Like, you have to know that yourself. You have to be able to plan out what this question is actually asking me. Okay, and what the steps are going to be required. Well, how do I write a vector equation? Like I said, well, you need the position vector and the direction vector. Well, how do I get a position vector? How do I get a direction vector? These are all things that you'll have to be able to come up with yourself, no matter what information you're given. So, and in this case, how do you find a point on the line? Well, maybe by inspection. What would I put in for X? Now, in some cases, there's going to be easier ways to do it. But in this case, I think it's by inspection. I could solve this for Y. I could move everything to one side, divide by 5, and solve it for Y. Plug in an X to solve for Y. But I could also just by inspection figure something out. So if I make X equal to 2, this becomes 4. And 4 plus 5 is 9. 9 minus 9 gives me 0. So if you didn't follow that, I mean, this is something that you're just going to have to kind of get on your own, right? Like, work through to the point where you say, okay, now I'm getting it. I can do this myself. But so I'm just going to say a point on the line is 2, 1. How did I get that? I got that by inspection, because the left side is 2x, or 2 times 2, plus 5y, or 5 times 1, okay, minus 9, which is 4 plus 5, which is 9 minus 9. So 9 minus 9, which is 0, which equals the right side. So I'm just finding some XY pair that satisfies the equation. And I did that by inspection. And there's no magic behind the numbers 2 and 1. You just start looking to see what you can make work. Sub 1 in for one of them and see if you can see if that'll make the other one work, kind of thing, right? Like, try some small numbers and you should be able to kind of work through that and figure that out. So that means I now have a position vector. Remember, points and vectors are not the same, and we think of them as interchangeable. Well, if this is a point on the line, then obviously that's a vector on the line. But when you're answering questions, you can't just assume that. If the question is asking for a vector, your answer has to be a vector. If the question is asking for a point, your answer has to be a point. That's a picky topic. So my position vector will be P, my direction vector will be D, and there it is, negative 5, 2, and that makes my equation, the position vector plus some parameter, so I'll choose t, negative 5, 2. Write the parametric equation of the line. So this was, oh no, it wasn't defined as a line L or anything like that. Okay, so parametric equation, I break it up into the x component and the y component. So the x is 2 minus 5t. How did I get that? 2 minus 5 times t, right? So if I'm thinking about this as expanding through kind of thing, the x is going to come from the 2 and the negative 5, right? That's where I'm getting the x from. And then the y is going to be the 1 plus 2t. Okay. Solve each parametric equation, each of the parametric equations for the parameter t, and then equate them. Okay, so each of the individual parametric equations. So I'll solve the first one, x equals 2 minus 5t. So I'm bringing the 2 to the other side, x minus 2 equals negative 5t divided by 5, negative 5. X minus 2 over negative 5 equals t. Next, the y minus 1 equals 2t. Obviously, this is something you'd be able to do in one step. And equate them. What does that mean? Well, this is t, and this is t, and it's the same t. That's the whole point. The parameter t is the same. I can pick a value for t and sub in. That's what the t means. So if it's the same t, I can set them equal to each other. So x minus 2 over negative 5 is equal to y minus 1 over 2. Okay. And this isn't just a coincidence. This wasn't just a random question. Turns out, flip your page over or flip to the next page. Turns out this thing has a name, and it's called the symmetric equation of a line. So in two space, the symmetric equation of a line, symmetric equations of a line are given by x minus x naught over m1 equals y minus y naught over m2, where x naught, y naught is a position vector to a known point, and m1, m2 is a direction vector for the line. As long as m1 and m2 are not equal to 0, why are they not equal to 0? Because you can't divide by 0. Okay, so this is the last of the different types of equations of lines that we're going to look at. Yesterday we looked at vector form, which is a pretty big deal. We looked at parametric form, which turns out is a pretty big deal. Then we looked at, today we just talked about the terminology of scalar. So that's one we've already seen, but now we're going to start calling it scalar. And this is the final one, symmetric. Symmetric's not all that useful to us. We'll see it a little bit here and there, but it's not as, it's probably the least sort of important, or going to be the least common for us of all four of those different forms of equations of lines, okay? And this is not a question that you'll really be asked. In the future, you'd be asked to write the symmetric equation of the line kind of thing, right? You wouldn't be asked to solve for the parametric equation for t and equate them. We were just doing that to introduce the idea of symmetric equations. But now you've got a 4, and if I give you 1, you got to be able to write the other 3. Or if I give you one of those other 3, you got to be write the other one, right? So you got to be able to go from every form to every other form. And a lot of what we're going to do is just going to be practicing that kind of stuff. A line passes through C and D given points. Write a vector equation of a line. All right, this is something we already did. What's different about this question? Anybody? They have 3 numbers. What does that mean? That means this is in 3 space. Okay, so this is the first time we're actually talking about lines in 3 space. So how do we write the vector equation of a line? It's the same thing. To write a vector equation, we need a position vector and we need a direction vector. Well, a position vector goes to a known point on the line. So my position vector can be the vector from the origin to either C or D. Doesn't matter, right? So I'll pick C because it's first. And I need a direction vector. And do you remember what we talked about yesterday? How we find the direction vector is going to be a vector between the 2 given points, just like we would find the slope between 2 given points, right? And how do I find a vector between 2 points? I subtract backwards. So CD is going to be D minus C. So 2 minus negative 3, which is 2 plus 3. Negative 1 minus 0. And 3 minus 1, which is our Z component, 3 minus 1. And that gives me 5, negative 1, 2 as my direction vector. Therefore, See, that wasn't too bad, right? X, Y, Z, because now I'm in 3 space, is equal to the position vector plus some parameter. Notice we like to use t times the direction vector. So almost the same as 2 space, but just now I have x, y, and z components of all my vectors and points and everything, right? Um, and let's see. How do I recognize that this is 3 space as opposed to 2 space? Well, because every vector is going to have an x, y, z. We can't mix and match. We can't have some that are 3 space and some that are 2 space. So, that should be something that is quickly recognizable, whether you are dealing with 3 space or 2 space. And it turns out there are going to be some pretty big differences between those two things in at least some of sort of what we're going to do and what's going to happen. Okay, so now maybe you're thinking or wondering or asking, what is a line in 3 space? Like, what is 3 space? Well, 3 space is the world that we live in, right? Like, we live in a world that doesn't just have 2 dimensions. I'm sure everybody's thought of this at some point. We don't just have an x and a y. You can move left, you can move forward, you can move up, down, right? So those are the 3 dimensions, the 3 directions that you can move. So let's take a look. Here is what GeoGebra looks like in 3 space. Okay, so I've got an x-axis, y-axis, and a z-axis. We have talked about this. We did 3-dimensional vectors in the previous unit, so this is not entirely new. We've seen 3D vectors, right? So I have to paste this in a bit of an odd way, so forgive me. Whoops. Control V. Now take a look at this equation. It has the point -3, 0, 1, which is written with round brackets, not square brackets. So GeoGebra will not recognize square brackets. Plus T. I have to use a parameter T. I can't use any other letter. GeoGebra is very picky about that. Okay, I'm going to do a separate video about the notation that GeoGebra wants and sort of write up some documents on how to type this stuff into GeoGebra, so you can see that for more of this. And then this is really important. There's a space here. I can't put the T right beside it. I can put a multiplication sign, which is not an X, is a dot in GeoGebra. So I could do that, or I can just leave a space, and then GeoGebra knows that I am multiplying. So T times my direction vector, and I'll hit enter, and you can already see the line. But watch what happens when I start dragging this around. I can actually see the line in space, can't I? Okay. So that's what a line looks like in 3 space. Okay, write the parametric equation line. And again, you'll notice that what we're doing is we are just doing all the same stuff that we've been doing, but we also have to know how to do it in 3 space. So the parametric equation of the line is going to be the x part, which is -3 plus 5t. Again, the -3 and the 5 is just where I got that from. Y equals, well, 0 minus 1 times t, so that's just -t. You could write 0 minus t if you want, but I don't know why you would. Okay, that's just the -t because of the 0 there. And then 1 plus 2t, and we always put it in a curly bracket like that. Okay, we don't just write them in space. We always put them together with a bracket. So there's your parametric equation of the line. Write the symmetric equation of the line. So remember, symmetric in 2 space, well, in 3 space, it's going to be very similar. Z minus Z naught over the third component of the direction vector. So this is going to be x minus -3 plus 3. So getting that either from here or from here, right? Over 5 equals y minus 0 over negative 1 equals z minus 1 over 2. So again, getting them from those values there. And in this case, I would probably not write it like this. I would actually write it like this. Simplifying that, the middle one there for y, right? Because that's just a better way of writing it. Determine if the point E is on the line. All right, let's give it a try. How are we going to do this? We're going to sub it in to each part, let's say each parametric equation, and see if I get a consistent T. That being said, I could, for this, I actually could use the symmetric equations because they are already solved for T, right? Each one of these things is equal to T. That's where they came from, if you remember the first time we did it. So T equals x plus 3 over 5. But if x is negative a half, I got negative 0.5 plus 3 over 5, which is 2.5 over 5, which is a half. We don't usually work with decimals, but in this case, the question was given in decimals, so it makes sense to work in decimals. The next one, t equals negative y, which is negative 0.5, which is a half. So far so good. Consistent t, right? But isn't it going to have to be consistent for all three parts? Being good for x and y is not enough. That would have been enough in 2-space, but not enough. So we got to check it against z minus 1 over 2, which equals, so the z component is 1, right? Z value is 1. So that's going to be 1 minus 1 over 2, which is 0. So the t is not consistent, therefore E is not on the line. Okay? Write the scalar equation of the line. How would we do that? Actually, this is not possible. Oh, and that is not how you spell possible. Not possible. There is no scalar equation of a line in 3-space. Obviously in 2-space there is. This is an important idea. In 3-space there is no scalar equation of the line. This is important because we have to know which of these forms make sense and which don't, okay? There is no scalar equation of a line in 3-space. So you might even be asked to do this as a trick question on a quiz or a test, and you have to say not possible or there isn't one. No scalar equation of a line in 3-space. Like you would have to say something like that, right? Don't just leave it blank. Never just leave it blank. So keep that in mind. That's a bit of a trick, but you heard it here. No scalar equation of a line in 3-space. All right, we're not quite done. We're going to do a little bit more. Determine if each pair of lines is parallel, perpendicular, or neither. Again, these are the kinds of questions where it kind of just throws it at you and you have to come up with a plan of attack and figure this stuff out, okay? So what do? Well, if they are parallel, then they will have a direction vector that is parallel. If they are perpendicular, then they will have a direction vector each that's perpendicular to each other, right? So if I can come up with vectors that are direction vectors for each of these lines, then I can determine if they are parallel or perpendicular. And if they're neither, then they're neither. How do we do that? Well, we're going to look at things, we did this before, things like the dot product. That's how we determine if two lines are perpendicular. They're perpendicular if the dot product is 0. So we already saw that, okay? So I'm gonna outline this nicely for our lesson. Line 1 for L1. For L1, it's in scalar form. This is in 2-space. I can't have one line in 2-space and one line in 3-space. Doesn't make any sense. So these are both in 2 space. And my normal vector is 214, right? Now I could change that to 1, 7 if I wanted, but I'm going to leave it as 214 because remember, the fact that it's a normal, it just means it is perpendicular to the line. So, so any scalar multiple of that will be perpendicular to the line. So vector D for line 1 will be anything that dots with that to be 0. So I could say -7 and 1, couldn't I? So 2 times -7 is -14. 14 times 1 is +14. Add those together, I get 0. Line 2. My direction vector, well, this one gives it to me, right? Oh, I should say D1. Direction vector 2 is just 7, -1, right? So it's given. And this is what I mean by, like, if I have vector form, it's giving me a direction vector directly. If I have scalar form, it's giving me the normal, which I can use to turn into a direction vector. Now, no, you don't have to write out the normal. You could just write out a direction vector. I mean, we did use that as like a little mini equation at the very beginning of the lesson, right? You don't have to write down both of these, but it's useful to think about them while we're just learning this stuff. So you might already know what the answer to this question is, but I'm going to go through all of it. So let's see. I am going to check the dot product. D1 dot D2 will be -7 times +7 plus 1 times -1, which is -49 plus -1, which is -50, which does not equal 0, therefore not perpendicular. Now we don't say that the direction vectors are not parallel. We'll say the lines are, not perpendicular. We'll say the lines are not perpendicular, okay? Because that's what the question is actually asking about. How do we determine if two vectors are parallel? And some people are going to say cross product. And so one of these things, we use the dot product and the other use the cross product. But whoops, we talked about this yesterday, not in 2 space. There is no cross product in 2 space. Okay. And there's probably an easier way because cross product is a little bit more work often. So for collinear, one has to be a scalar multiple of each other, right? So remember, for collinear or for parallel, there must be a k value such that D1 equals k times D2. And there is one, isn't there? So I can do, where am I here? D1 times, D1 is equal to -1 times D2, right? So in other words, k equals -1. Therefore, L1 is parallel to L2. Okay. What's the other thing that we actually could have done here? They're parallel if the dot product of the direction vector of line 2 with the normal of line 1 is 0. Think about this. This is where we start to really understand these properties and start to be thinking in vectors really nicely and thinking about the properties of the dot product and eventually the cross product, that kind of thing. Okay, so if I dot product the direction vectors, then they're perpendicular, and it's 0, sorry, then they're perpendicular. If I dot product the normal with a direction vector, then they are perpendicular. But if the direction vector is perpendicular to the normal, it is going to be in two space, it is going to be parallel to the line as well as the other direction vector, right? So there's another thing to think about. I'm not going to go any further with that, but that's something else to kind of think about. And that in two space, that will definitely work, right? Okay. Finally, last question, B. This is the same thing. Determine if they're parallel, perpendicular, or neither. And this time we're given symmetric form and parametric form, but again, we are working in two space. Okay, so for line 1, how do I find a direction vector from symmetric form of the equation of a line? And this is where you have to be able to do this stuff. I can go back and I can think about how we developed the symmetric form originally and how those values came from the direction vector in vector form, right? That's where they came from. But hopefully, eventually, you'll just kind of remember. And for this one, we know that it comes from the coefficients of the t parameter. And so there you go. Okay, so now d1 dot d2 equals 2 times negative 3 plus 3 times 2, which is negative 6 plus 6, which is 0. Therefore, L1 is perpendicular to L2, 2, comma, they are perpendicular. Okay. A common question is, do we have to do both? Like, can't I just by inspection show, like, see that that's not going to be 0? Why do I have to show that? Yes, that's true. If the question just says determine if they're parallel and perpendicular, and you can by inspection figure out which one it is, you just have to show that. If the question somehow is worded to say and prove that it is not parallel or not or something like that, then I mean maybe you would have to show more. We don't tend to ask that, but right, like there could be other. It could say show that the following are not perpendicular, and so in that case, it's asking you to use the dot product, right? But for a question like this, if you already know just by inspection which one of the things it is, then you could just go straight to that one. You don't have to do both. Okay. Now, if it's neither, you would have to show that both don't work. You would have to show that the dot product is not 0, and then you'd have to just state that they're not a scalar multiple of each other. There is no such k that d1 is equal to k times d2. You would just say that. And I think we saw an example of that yesterday. Okay. So same worksheet from yesterday, some different questions. Nothing wrong with the rest of the questions on the worksheet. They are good extra practice, so it's only asking you to do A and C, but if you want some extra practice, I believe the rest of them are fine. And that is that. So that is equations of lines. Tomorrow we're moving on to something new, not just equations, and that's going to make our world a lot bigger. And so keep that in mind that we've done 2 days of lines, we've done 4 different forms of the equation, and this is stuff we need to know. You don't want to start falling behind already. We need to know scalar, vector, parametric, and symmetric, and how to get direction vectors from them, how to get normal vectors from them, how to get points on the line, how to determine if a point is on the line, all those different things, how to determine if they're parallel or perpendicular, blah, 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 blah. All these different things are all the kinds of questions we want to be able to do, and the sort of, easier it is and faster you are at figuring out how to do those things and what it means about their properties, the better off everything else we're going to be asked to do, the better off you're going to be with all of that, okay? But that's it. That is equations of lines in 2 space and 3 space.